Okay. All right. So we have a particle moves through a circle. Through what angle and radians does it rotates if it moves through an arc length of 2.5 meters? This is not even a physics problem. It's a trigonometry or geometry problem. So it's a radius. It's a radius of 1.5, and 2.5 is the sector length, and we're trying to find the angle here. The angle. This is not even. I mean, this is s equals r theta. This is s. This is r. This is theta. So the angle is s over r. The s in this case is 2.5. The radius is 1.5. This angle, though, is in radians. So there are 2 pi radians in 180 degrees. So you have to take your answer and multiply by 180 over 2 pi for that. And you said the answer's at the bottom? Okay. So if you got a calculator, we can calculate that.
Getting this out.
Sorry, it's 180 over pi.
Oh, 180 over pi?
Yeah, okay. not 2 pi. That's me thinking about something from what you're doing here. Okay, so that ends up being 95.5 degrees.
Wait, is it just, wait, so 2.5 divided by 1.5, I get 1.666, and then multiply that by 180 and divide that by pi.
Yeah.
Okay, I see it now. I think I did something weird with the division or something. All right.
Yep. All right. So we got number 2, something about a grinding wheel. All right. Grinding wheel initially at rest is rotated with constant angular acceleration alpha equals 5 for 8 seconds. The wheel is then brought to rest with uniform negative acceleration in 10 revolutions. Determine the negative angular acceleration and the time required to bring the wheel to rest. Okay. So there's some equations here. Did you get do you happen to have a rotational kinematics equation sheet?
Rotational kinematics equation sheet. Yes, I do. I will pull that up right now.
Okay. Because I'm gonna pull mine up here. There's a ton of parallels to regular kinematics. So the angle is omega times t. Omega final equals omega initial plus alpha t. Oops. Omega final squared equals omega initial squared plus 2 alpha theta. And then theta equals theta initial plus omega initial t plus 1/2 alpha t squared. Okay. Now, does this help us? Yeah. So they give you alpha and they give you time. So we know, and we know it's not moving. So we can find its omega final. Its omega final is omega initial, which is 0 because it's at rest, plus its alpha, which is 5 times 8. So it's moving at 40 radians per second.
Okay.
Determine the negative angular acceleration required and the time needed to bring the wheel to rest. So it's currently moving. Okay.
Okay.
So that's so its omega final is really now like it's since it's moving, it's now omega initial. So the omega initial, like we consider this point later in time, is 40 radians per second, and we use this equation here on the left because the final omega final is 0 because it goes back to rest. So omega final squared, that's 0, equals 40 squared plus 2 alpha. We don't have alpha. That's what we're trying to find. Theta, though, is 10 revolutions. So 10 revolution, and 1 revolution is 2 pi. So that's your theta there. So we're solving this for alpha.
I see.
So to do that, we move this over. So it's negative 40 squared. And then we divide by this 2. And then we divide by this 10 times 2 pi over here. And let's get that number and then compare it to the one at the bottom.
So negative 40 squared is, would this be a negative or a positive on the top?
It's negative because you're moving it over to the left. You're solving for alpha over here.
So negative 1600 divided by, what is that, 2 times 10 pi. So, all right.
Okay, so let's see if that is
Correct.
Yeah. Before we move on here. No, it says it's minus 2.26. Oh, times 10 squared? Oh, that's number 3. Oh. So the number 2 doesn't have the answer, just has the time. So we got to use this answer to find the time. Okay. So I'm not sure if that's it. So the time, you look back, like which equations have time? Well, this one obviously has time. We can use this one up here though. Omega final equals omega initial plus alpha t. The thing was spinning. That's its omega initial. That's the 40. That's the 40. But the final is 0. So it's omega final equals omega initial plus alpha t. This is 0 because it goes to rest. This is 40. And the alpha is what we just found, the minus 12.73 t. And we solve that for t. So t equals minus 40 over minus 12.73. And yeah, we're going to be pretty much right on that, the 3.1 seconds there. Yeah, approximately 3.1 seconds.
All right, let's go on to number 3.
Okay. These questions would have been really good to do to start at some point whenever you started learning this unit. If that's ever an option in the future, you will get way more out of those problems we do online than if we do these first. Okay, so an angular speed, that's omega. Omega initial is 3,600 revolutions per minute. We have to convert this to radians per second. So 1 revolution is 2 pi radians. 1 minute is 60 seconds. Like that's got to be like you got to know that right away. Find the constant angular deceleration of the centrifuge. So it comes to rest. We don't know how long it takes. We don't have time. So we have to go find an equation that does not have time in it. So the one that's going to work here is omega final squared equals omega initial squared plus 2 alpha theta. Okay, and we're trying to find that value. So we better have the others. So the omega final, that means omega final equals 0. That one's 0. Okay, omega initial is this value we just found. Okay, so that's the 3,600 times 2 pi divided by 60 squared plus 2 alpha. Alpha is the thing we're trying to find. Theta is the angle. The angle. So it rotates 50 times.
I see what you mean. Okay.
So the theta is not 50 though, but theta is 50 times 2 pi, because one revolution is 2 pi.
You gotta multiply that by, oh, because it rotates 50 times. Okay.
Each rotation is 2 pi. So now we're solving for alpha. So alpha equals 0 over here, minus 3600 times 2 pi over 60 squared divided by 2 times 50 times 2 pi.
And once we find that alpha, do we plug it back in and then multiply it out?
Nope. That's what we're trying to solve for. We're trying to find the constant angular deceleration. That's
that's all
alpha.
we're looking for. Okay.
And the fact that it says the deceleration, that just means that it's negative.
So that means that just the answer itself is going to be negative?
Yep.
Okay. All right.
All right. So we got minus 3600 times 2 times pi divided by 60 squared. That's radians per second squared.
That is correct. All right. On to number 4. Airliner at terminal.
Yep. Let me snip this in. Okay, determine the angular velocity after 10 seconds. Okay, so we're doing something with time. Angular velocity, that's omega. Okay, the rotator one has initial clockwise angular velocity. So omega 0 is that. That's omega 0.
Mm-hmm.
And the angular acceleration is, that's alpha is the 80. So they want the angular velocity after 10 seconds. That means they're giving you time. So you want to use an equation that has time in it. One of those equations with time is, if I can get back to it, is where was I looking? Okay. Is we've got, yeah. So omega final equals omega initial plus alpha times t. So your omega final is what we're trying to find right here. So omega final equals omega initial, which is 2000. It's in the right units, radians per second, plus alpha, 80 radians per second squared times 10 seconds. So that is 2,800 radians per second. Okay, so then how long does it take the rotor to come to rest? So it's spinning that fast.
So I got that. And now, how do we find the time in this case?
Yeah, great question, because I'm thinking about that too. So the only equations that have time in it is omega final equals omega initial plus alpha t. Oh, you know what? I did this wrong. I'm sorry. This is not correct. It says with angular acceleration, the engine's rotation slows. So that means that this is actually negative.
Negative?
Yeah.
Oh.
So that's wrong. That should be 1200 radians per second.
How'd you get, wait, so 80, 800, negative. Oh, okay, 1200.
Now we can do this because omega final is it's getting to 0. Initial is 1200, and we know that it's decelerating at 80 t.
And now we're looking for that t, right?
Yep, t is minus 1200 over
by
minus 80,
80,
which is like 15 seconds.
I'll check the bottom for that. So 18 seconds. It says 25 seconds.
So they're including the 10 seconds prior to it that happened prior to it?
So there's 15 plus 10, I guess.
I guess I think the way it's worded, you're it's 15 seconds from this part B.
Mm-hmm. All right.
All right, we're on to a new question. Question 5. Race car travels, doing something here. Race car's moving. Race car travels in a circular track, radius 200 m. If the car moves with a constant speed of 80 meters per second, determine its angular velocity. So angular velocity W is equal to V over R.
Yes.
I think. Yeah. That seems reasonable. Yes, W is V over R. So we have its velocity. Its velocity is 80. Its radius is 200. They're all in the right units. That is your W for that. .4. Yeah. Let's check. Is that right for this one? Question 5.
Yep, 0.2, 0.4 radians per second.
Yeah. Okay. And then it's tangential acceleration. A tangential. Ooh, a tangential. Just I'm at drawing a blank here because I don't see any formulas for tangential acceleration. Let me do another search here.
I can check my slides and see if he has anything on that tangential acceleration.
It's like
okay, so tangential acceleration is A tan equals V over T equals R change of W over T change in T.
yeah, but we only have so many quantities here. We have basically two quantities. We have radius and V, and now W. So we don't have time.
Yeah, I think that's the problem. A tangential equals R times alpha. Does that help?
Well, we don't have alpha. Alpha is W. Alpha also relies on time. I'm going to just do a search on this question. I'm sure it's out in the interwebs somewhere. And we'll see if there's a solution for this. Yeah, you need time.
Wait, it doesn't have time at all.
Yeah.
That's got to be a bug or something.
So the instructor borrowed this from a question where they ask you for, they give you an increase. They say it goes from 80 to 95 meters per second in 10 seconds. Then you can find alpha. You just can't do it with the given information, as far as I can tell.
Skip this one, I guess.
Oh no, you know what? It's there. I'm sorry. Question 6 refers back to it. Maybe it's tangential acceleration 0. What is the answer to it?
It's like 7.5 times 10 to the negative 3 radians or something like that.
Mm-hmm. Well, that assumes you have some sort of time, which we don't have. Okay, well, let's try to do question 6.
It says in 10 seconds from 80 milliseconds.
Yeah, meters per second. Yeah, and you do need time to do these calculations. So
it's got a gaping hole in it.
All right, so let me snip in 6, and we'll see if we can come up with something reasonable here. So the acceleration is v final minus v initial over time. So that's 95 minus 80 over 10, which is 1.5 meters per second squared. Now, this is where now is where we can actually do something. The angular acceleration is a over r. Well, you have a. Your a is 1.5. Your radius is, from the previous problem, it's 200. So that ends up being that ends up being 0.0075
whatever, yeah.
radians per second squared.
And
Right?
that's 7.5 instead of -3 power.
Yeah. Now it says determine the angle that the car moves through in this time. So one of the equations with angle in it is W final squared equals W initial squared plus 2 alpha theta. So we have alpha. That's what we're trying to solve for. We're going to solve for that variable. And we need the W final and the W initial. So the W final is V over R squared.
Yes.
That's what W equals V over R. And this is V over R squared as well, plus 2 alpha theta. So the V is the initial velocity. That's the final velocity. The final velocity was the 95. So that's 95 over 200, because that's the radius squared, equals the initial was 80 over 200 squared plus 2 alpha, which is the 0.0075. And we can solve this for theta. So we can move this to the other side and divide by this number here. 95 over 200 squared minus 80 over 200 squared, all divided by 2 times 0.0075. That angle, though, is in radians, so the number you get might not mean much until you convert it to degrees. Does the answer appear in degrees or radians for 6? No, it's in radians. So this ends up being 4.4 radians.
All right. That is correct. Let's move on to that next problem.
Next problem is number 7. The tire and radius. Tire 0.5 meters in radius. Tire 0.5 meters in radius, rotates at a constant rate of. So this is your R. This is your omega. Your omega is 200 revolutions per minute. And you have to know by now that you got to immediately convert to radians. 2 pi radians in 1 minute, there's 6 seconds. Find the speed and the acceleration of a small stone lodged in the tread of the tire. It's out of edge. So this thing, we want V tangential or V, and then we want A tangential as well. So the V is the easier one to do. We know that W equals V over R. Okay, so V equals W times R. We have W. W is this 200 times 2 pi over 60, and we know the radius is 0.5.
So we'll multiply those out and we get the velocity.
Mm-hmm.
Oh, is that that's all it's asking for, right? I keep expecting these to be multi-layered.
That's the speed. We have to find the acceleration.
2 pi and then divide by 60. Multiply that by 1/2. 10.47 for for the velocity. Now we want that acceleration. What's acceleration equal to
Well,
again?
well, again, like usually we need time because so alpha is equal to acceleration over r, but we don't have alpha. Um, so this is like it's like same as the previous one. I'm like, what we're gonna do? So let me just go find this question. Some physics ninja has probably already figured this out, and we can help do that. So, oh, the acceleration on the edge, and then maybe that is what was needed in the previous problem here. Now that I see that, um, the tangential acceleration is v squared over r.
Okay.
So this was 80 squared over 200. This one down here is the same thing. Acceleration is v squared over r. And your v we just found, it's that number there, whatever that number was. 200 times, I'm sorry, yeah, 200 times 2 pi over 60 times 0.5 squared over your radius, which is 0.5. I think you said this was 10.5-ish.
This one, yeah, it is 10.5 meters per second.
Yeah, so this one is, it's going to be a big number, but 221.
Sounds about right. On to number 8.
Number 8.
Oh, yeah, that gets 218 meters per second.
It's just rounding. I mean, it's within 3 over 200, so that's like 1.5%. That's pretty good.
Okay.
For your answer. Okay, driver of a car traveling 30 meters per second applies the brakes and undergoes a constant negative acceleration 2 meters per second squared. So this is V and this is A. How many revolutions does each tire make before the car comes to a stop? And the radius is 3.3. Okay, so we know that W equals V over R.
Mm-hmm.
So we can find W here. W is 30 over 0.3, which is 100 radians per second.
I think that's correct.
Okay, and then alpha is equal to A over R. Alpha is 2 over 0.3. So that one does not work out very nicely. It's 20 over 3 radians per second squared. And it's negative. It's negative because it says negative there.
Weirdly enough, when I divide by 0.3, I get 6.666 or whatever.
Yeah, so that's fine. So now we're trying to figure out how many revolutions does the tire make. So that's theta. That's theta. So there's this omega final equals omega initial plus, did they give us time? Nope. So our equation is the one that's the squared equation. See if I can find that. There it is. So we have omega final squared equals, omega final squared equals omega initial squared plus 2 alpha theta. We're trying to find the angle there. We have alpha. We have omega initial. That's what we just calculated. What is omega final if it comes to a stop? Zero.
Oh, just zero?
Because not rotating, just sitting there doing whatever. Just on their own. So 100 squared plus 2 times negative 20 over 3 times theta. So when you solve for theta here, theta equals minus 100 squared over 2 times minus 20 over 3. That is going to be in radians.
And you end up getting something like, like 6. Yeah, I get theta is 119 revolutions.
Actually, it's yeah. So is that close to the answer?
I think so. Let me check.
I get 750 for the number of revolutions, or 750 radians.
Oh, and then you
Oh,
put back in
750 radians. What is the answer in?
It says revolutions.
So that's divided by 2 pi radians in 1 revolution. So you said about 119. That sounds right, because that's divided by that. Yeah, so 119.
On number 9.
Number 9. Young David experimented. Okay, he found that he could develop an angular speed, that's omega, of 8 revolutions per second in a sling that's 0.6 meters long. If he increased the length to 0.9, he could revolve the swing only 6 times per second. Which angular speed gives the greater linear speed? So I think we're supposed to assume that this is the radius. The radius is 0.6, and then when it's 6 revolutions per second, the radius is 0.9. So they want you to calculate the v associated with each of these. So w is equal to v over r. So that means v is equal to r times w. So we have to multiply these two numbers together. 8 times 0.6, that's 4.8. So v equals rw down here. 6 times 0.9, which is 5.4. And that's what we're choosing between. Which one is better? Well, it's this one, because it's bigger. The velocity is bigger. Sorry, if you're not following this, let me know. I mean, I'm pretty tired, but hopefully this is still making some sense.
It's still making sense to me.
Okay, that's part A. Part B is the centripetal acceleration, which is v squared over r of the 8 revolutions per second one. So we need its v. Its v is over here, 4.8 squared. Radius is 0.6. That is whatever it is, 4.8 squared divided by 0.6. Okay, 38.4. And that's meters per second squared. And then the other one, you have to find the centripetal acceleration of the other one. That's v squared over r. That's the 5.4 squared over 0.9.
For B, it says acceleration equals 1.5 times 10 to the something meters squared.
So it's possible that they're not using that as the radius. They might say the radius is 0.3, and that radius might be
Something completely different.
0.45. Well, it's half. I mean,
Yeah, different number.
it doesn't give us anything in here to know that. So that would change. That cuts each of these numbers in half. That's 2.4. That's 2.7. That changes this one. That changes this one to 2.4 squared over 4 over 0.6.
For whatever reason, for A, it doesn't even ask for the actual like calculation. It's just asking. It just wants you to know there's a greater linear speed with larger sling. Yeah.
So I've got 9.6 for the first one, acceleration.
Mm-hmm.
Is that right? Does that line up there? Actually, I got the answers down here. I can see. 1.5 times 10 to the third.
Is this all negative or something?
No. Let me search for this. I'm missing something here. Oh, I'm missing a 2 pi. Oh, bless it. Okay, so the revolutions, I didn't convert this to I didn't convert this to, because 1 revolution is 2 pi. Same thing down here. This one has a 1 revolution is 2 pi. So all these numbers change. Let me see if I can clean some of this up here. This is all wrong. Get rid of all that. Get rid of all that. So and it does look like they use the 0.6 and the 0.9. I still can't tell you for sure. So the radius is 0.6. The W is the 8 times 2 pi, and that ends up being I'm getting like 30.16. Is that I mean, you're getting something similar to that?
Yeah, I got that.
30.16. Okay, and then the other one is 0.9 times 6 times 2 pi. Which is 33.93. So now the centripetal acceleration is the v squared over r. That's the 30.16 squared over 0.6. And you said you had a number for that.
Yes.
Over 0.6. So that ends up being 1516, 1516, which does seem consistent because I think it's in yeah, it says 1.5 times 10 to the third. That's consistent with that. The other centripetal acceleration is this 33.93 down here, because it's the second number we found, 33.93 squared, and divided by 0.9. So that's 1279 meters per second squared, which is pretty consistent with what they wanted.
All right. Number 10.
10. We got elevator. Okay. The downward motion of an elevator is controlled by a cable that unwinds from a cylinder of radius 0.2. What is the angular velocity? So that's W. When the speed of the elevator is 1.2 meters per second. Okay, so W is equal to V over R. We have the velocity, it's 1.2. The radius is 0.2. Looks like it's 6 radians per second. I don't know, that was really straightforward for where it looks like that should have been like question 2.
Yeah.
That's it for that. 11. All right. 60 centimeter diameter. So this is not in the right units. That's a 0.6 meter. Cut it in half. That gives you your radius. Wheel rotates with constant angular acceleration. Alpha equals 4. It starts from rest and makes an angle of 57.3 degrees. That's theta. That's in the wrong units. So probably pi over 180 to get it into radians. At 2 seconds, find the angular speed of the wheel, the linear velocity and tangential acceleration of P, and the position. Wow, that's a loaded question. So the W. So W final equals W initial plus alpha times T. Let me just check that. Is it alpha? Yeah. Plus alpha T. So we have the, we're trying to find the omega final. We know it's currently at rest. We know that alpha is 4, and we know that T is 2. So this is 8 radians per second. Is that correct? Yeah, that's correct for part A. Okay, the angular speed of the wheel. So we know that alpha equals A over R. That's A tangential. So A tangential equals alpha times R. Alpha is 4, and the radius is 0.6 over 2. So that is 1.2 meters per second squared.
$1.2 is correct. Meters per second squared.
Yep. And then the last one there wants the angle. The angle is theta final equals theta initial plus omega t plus 1/2 alpha t squared. Your theta initial is 57.3 degrees. Your omega initial it was initially at rest. So it's 1/2. Your alpha was 4. T is 4. Oh, this is in the wrong units. This is in, this shouldn't be, you need to multiply this by pi over 180.
Mm-hmm.
And then this whole answer is going to be in radians. So you take this whole answer and you multiply by 180 over pi to get it back to degrees. Let's see if that works itself out. Plus 1/2 times 4 times 16. Okay, 33 times 180 over pi, and 1890. That doesn't look right. 516 degrees. Pi over 180 plus 1/2. Alpha is 4. Is alpha 4? Yeah.
Should come out to be 516 degrees.
Yeah, I'm not seeing that. Okay, let me check a reference. Maybe they use the other alpha equation. Maybe they use the one omega final squared equals omega initial squared plus 2 alpha t. No, 2 alpha theta. So omega final was 8 squared, 0 squared plus 2 alpha. So that's 64 divided by 2. Alpha was 4, so that's 8 radians. 8 times 180 over pi is 458. Is that what you said?
Yes.
Okay. So they use this equation to solve for theta. And then you get 8 radians and you multiply by 180 over pi to get it in 2 degrees.
I think answer thing says 516 degrees.
Oh, you have to add the initial 57 to it.
Oh, all right.
And that gets you to 516.
So, all right.
I think that's everything I wanted to work on today.
Great. If you ever need a time that's not available, just let me know and I'll add it for you if I'm available. Thanks, Jack. Have a good night.
Thank you. You too.
Goodbye now.
Appreciate it. Bye-bye.